Welcome to the video in which I present my paper entitled A Comprehensive Revealed Preference Approach to Approximate Utility Maximization. First of all, thank you so much for agreeing to watch this video. I think that's the right way to put it. I promise not to take too much of your time. It will take, I'm going to aim for about 20-minute presentation. We'll see how it goes. Now, this is an ongoing research and it is very much work in progress. So any comments, suggestions are very welcome. The very point of this video is really to somehow encourage people to read the paper and then give me comments if possible. So that's really what I'm aiming for. Just a little tiny comment before I begin. This is a short presentation. It won't have many references and citations, and just to save space and time, I'm quite generous in the paper itself. So if you've done anything related or haven't, there's a very good chance you're being cited and given the credit that you definitely deserve. So without further ado, let me just dive into the presentation itself and the paper itself. So the idea of the paper is really quite simple, and it is to come up with a quite flexible method that will allow us to study utility maximization, even though the data that we have can may be inconsistent with this hypothesis. Right. So maybe just to motivate what I want to say and what I want to talk about today is, well, if we think about utility maximization, it's definitely one of the least controversial assumptions that, virtually everybody makes in economic analysis. But at the same time, the problem with this restriction, with this condition, with this assumption, is that when it comes to empirics, it doesn't do that well. In the sense that if we look at choices of individuals, they seem not to be consistent enough to be congruent with utility maximization hypothesis, and that's kind of an issue, right? There are at least two ways I can think of dealing with this issue. One is quite controversial and pretty drastic, which is we can just throw it away and try and replace it with different models of decision making, either deterministic or stochastic. The issue obviously is that, overhauling the whole economic analysis is a daunting task, and I'm not sure we should be doing it straight away. On the other hand, there's this kind of practical issue with stochastic choice, meaning that it kind of requires a lot of data that is difficult to gather on an individual, even in experimental settings. Right. So there are these two issues which are difficult to tackle. Now, the other way of approaching this is maybe this slightly more moderate way of addressing this problem is just simply accept the fact that utility maximization, essentially by assumption, is just an approximation of how people behave, and nobody really believes that it's an exact hypothesis. And based on this observation, we may try and come up with methods that are a bit more flexible and may allow us to study utility maximization, even if the data isn't fully consistent with this hypothesis. And given the title of this presentation, you probably expect that this is exactly where I'm going. And so what I want to do in this, when I'm doing this paper, is really is focusing on the model which I call approximate utility maximization, which is far from being new, but I want to use it in a slightly different way. So just to be precise what I have in mind, throughout this presentation, I will assume that the researcher has access to a finite data set O, which just consists of pairs AX, where A is a menu and X is a choice selected from that menu. Now, what I mean by approximate utility maximization, well, the question is, when can I find a utility function U and a positive threshold function delta such that X is chosen from A if for any other alternative utility of A is not sufficiently lower than utility of Y? So in some sense, it's approximate utility maximization in the sense that individuals are not exactly maximizing their utility, but they're kind of close to doing it, right? There's some threshold up to which they're maximizing their utility. Now, for those who are somehow acquainted with interval orders and threshold representations, they obviously know what this is. The reason I'm calling it differently is because I really want to focus on the utility function that I will identify with true preferences of the individual. That is as if the exact maximization were possible. And I really want to study this object. And so this is really the only reason why I want to call it slightly differently, so that we focus on a different object. Just to give a brief overview of the results, what I'm going to be doing in this presentation is really just showing this equivalence. Right? So essentially just explaining that if you want to think about approximate utility maximization defined as previously, what you're really talking about are non-transitive indifferences. And that's really the only content of a model like this. What is also true, kind of we get it for free, but I will not be mentioning this in this presentation, is that it's also equivalent to the very classical notion of satisficing, which is just nothing else but choosing an option that is good enough in some well-defined sense. Again, I won't be talking about this. I'll just be focusing on this one equivalence between approximate utility maximization and non-transitive indifferences, just trying to explain what I really mean by approximate utility maximization. What really follows from this result is that we can really say a lot about the utility function u, even though we know that the agent may not be fully maximizing it. We can elicit the true utility from the data. We can make out of sample predictions. We can do welfare analysis. And there are also a few interesting applications that are presented in the paper, but will not be discussed in this presentation just for the sake of time. Now, before I continue, one final question would be, why should we care about non-transitive indifferences? I guess this is worth investigating. And so a few interpretations just showing that non-transitivity of indifferences isn't that absurd, and there isn't really anything irrational about having non-transitive indifferences. So the first one was already mentioned, that's satisficing, which has a very direct link to approximate utility maximization, as I mentioned. The second one, which is kind of was the main inspiration for this work from the very beginning, is the issue of imperfect discrimination, in which individuals may not be able to discriminate between goods or objects perfectly. So this really goes back to antiquity and Sorites paradox, that when a heap of sand stops being a heap of sand, and this type of thinking then applied to economic analysis. Finally, we have this concept of imprecise preferences, which very roughly speaking is this idea that indifferences can be a bit fuzzy, or at least much more fuzzy than strict preferences. And so one manifestation of this could be, for example, that individuals prefer to give intervals, evaluate lotteries using intervals of certainty equivalence, rather than individual values, which kind of shows that there is some fuzziness around indifferences. Even though distinction between money and lotteries is quite straightforward, right? So it's different from imperfect discrimination. Okay, now before I go to the result itself, I wanna present some classic results in revealed preference theory. Actually, just one classic result in revealed preference theory. On the one hand, just to give you enough foundation to understand what I'm doing and somehow to appreciate my contribution, and then also in the meantime, I'll be slowly introducing new notation that is kind of necessary. Well, it's necessary for my result. So let's start with basic notation. X is just a space of alternatives. I impose almost no assumptions about X. These can be lotteries, sets, consumption bundles, acts. Choose your favorite and stick to it. A menu is nothing else but just a non-empty subset of X. Again, I will, as most of the result, at least definitely the main result, assumes very little about menus. A data set is just a finite set of pairs AX, where, as I mentioned previously, X is a choice made from A. So this is the information that the researcher actually has, that gathered from an experiment or the field or whatever you like. Now I'll be talking about different choice models, well, two to be precise in this presentation, but to give you a general definition of what I mean by a choice model, well, it's just a correspondence that maps different menus into choices from those menus, right? So this is as standard as possible. Also, when it comes to rationalization, this is the notion of rationalization that I have in mind. So a choice model rationalizes the set of observations O whenever it's consistent with it. What I mean by this is that whenever you observe X being chosen from A, well, it better be that X actually belongs to C of A. So it's as standard a definition as possible. So let's just now focus on this most fundamental question in revealed preference theory, which is when can we rationalize a set of observations with utility maximization? What I mean by this is when can I find a utility function U such that this correspondence rationalizes the observations as defined previously, right? So whenever you see X being chosen from A, then X belongs to a set defined like this for that utility function. Now, the immediate observation is that this question is vacuous because if you take a constant utility function, you can rationalize absolutely any set of observations. So that's not very interesting. Just so to make it a bit more interesting, to gain some traction, the usual thing to do is to impose some extra conditions on the utility function, like strict monotonicity. And this is exactly what I'm going to do now. Now, the only difference to what is usually done is because I'll be discussing different models of choice, I want to have a definition of monotonicity that can be applied across different models without really specifying what the model is. And that's why I propose the following definition. So I will take a correspondence gamma that maps X2 to itself. I'll give interpretation in a second. And then I will say that the choice model C is gamma monotone if for any menu A, the following condition holds, right? So whenever gamma X intersects a menu or the menu that you selected, then it can never be that X is chosen from A. Essentially what this means is that gamma X is somehow a normative assumption that the researcher is making about the choice, and gamma X is simply, how can I put it? Options is a set of options that the researcher considers to be objectively superior to X. And that's what we mean. Now, it's a nice definition for two reasons. One reason is that it really just is choice. It's like it's model independent, so it really can be applied to any model of choice. And second of all, if I think about utility maximization, it coincides exactly with strict monotonicity of the utility function that I have in mind, right? So there's a nice relation there, and it's an if and only if condition. Right, so this is the exact definition you want to have if you want to talk about utility maximization, and then I'm going to just simply apply it to different models of choice as well. I assume very little about gamma. Specifically, some values of gamma can even be empty. I don't really mind. What I do assume, though, are these two, I think, non-controversial conditions. One of them is that X is never strictly objectively preferable to itself, which I think is quite... it's a good assumption. And the second one is a retransitivity type condition. So if Y is objectively better than X, then anything objectively better than Y has to be objectively better than X. Then if X is uncountable, so if the space of alternatives is uncountable, we add one more separability condition on gamma, but it's just technicality, so I will skip it. And it doesn't really play much of a role in the results. Just to give you some intuition, a few examples, more is better is one possible way of looking at it. So if I think about bundles, if one bundle has more goods in all dimensions and strictly in one dimension, I would say it's objectively better than X. Stochastic dominance, pretty much the same idea. If you want to analyze choice over lotteries, then if lottery Y is stochastically dominates strictly X, then it's objectively superior. That's a different assumption, normative assumption you can impose. Another one which makes less sense maybe with utility maximization, but is quite interesting when you want to talk about approximate utility maximization, is this idea of imperfect discrimination, where you say that a bundle is superior to X if it's greater in each coordinate and sufficiently, like significantly greater in at least one of the coordinates, right? So the ratio of the goods in that dimension is at least greater than some constant, right? So for those who know Weber-Fechner law from psychology and psychophysics, this kind of is where the inspiration is coming from, right? These are just examples. So now we can actually go back to the original question and once again try to answer the question, when can we rationalize a set of observations with utility function, but now taking into account that the choice correspondence has to be gamma monotone. So we add this one extra condition to get some extra traction. And it turns out it actually gives us enough traction to get some testable implications of utility maximization. And how do we go about it? Well, we start with revealed preferences being defined. So I will say that X is directly revealed preferred to Y, which I denote by this, whenever X was chosen when Y was available, right? It's as standard as possible. I can also have a strict version of this relation, and I will say that X is directly revealed strictly preferred to Y whenever X was chosen when something objectively better than Y was available. Right, so essentially X was chosen over something objectively better than Y. That's when I say that X is directly revealed strictly preferred to Y. Right, so it's a very standard and I think not at all controversial definition. Just to get some intuition, let's think about this graph, two-dimensional commodity space. Let's think about this imperfect discrimination example. So that's how I define gamma, like in 2 slides ago. So for this vector Y, for this bundle Y, the gray area essentially represents the set of all objectively superior bundles, according to my definition. So that's how it looks like. Now, if we add a very standard budget set and we say that X was chosen from this budget set, then straight away we already know that Y has to be weakly inferior to X because X was chosen when Y was available. But notice that gamma Y intersects the budget set. So actually we can say more. We can say that Y is strictly inferior to X. And the same really applies to every single point in the gray shaded area because the same condition holds, right? It's a very simple algebra to figure this out. And so we have this nice kinked shape. Now, why is this relevant? Because revealed preferences really contain all the information about the utility function that rationalizes data. In the sense that if X is weakly preferable to Y, then U of X has to be weakly greater than Y. If X is strictly preferable to Y, U of X has to be strictly greater than Y. And so from this, you get almost immediately a necessary condition for utility maximization, which says that there can be no sequence of elements in the space of alternatives such that Z1 is weakly or strictly preferable to Z2, Z2 is weakly or strictly preferable to Z3, and so on and so forth, and the final element is strictly preferable to the first element. Right, so necessity, is immediate, just following from the previous observation, because if we had a sequence like this, then Z1 would have, the utility of Z1 would have to be strictly greater of utility of Z1, contradiction. Interestingly, Nishimura and Kwa also show that this is also a sufficient condition. So really, utility maximization is contained in these two lines of the generalized axiom of revealed preference, which is what GOP is really standing for. Now, the reason I want to discuss this is because this condition shows how critical is transitivity of indifferences for utility maximization, right? Because notice that the only cycle of revealed preference that GOP is allowing for is the one generated by the weak preference relation only, right? In this case, because we know that utility maximization requires transitivity of preferences, this has to imply that all these elements in that cycle have to be indifferent to each other. But as I mentioned at the very beginning, assuming non-transitivity of indifferences is not that absurd, and in some cases can actually be a sensible thing to do. So the question is, what changes if we relax this condition and this condition only? And that would leads me to my results. And so really what happens when you relax non-transitivity of indifferences is that now you can admit cycles in which some alternatives can be ordered with respect to P, but not all of them. Right, so if I have a cycle in which some alternatives are ordered with respect to weak relation and some of them with respect to strict relation, that's kind of okay because I allow for indifferences to be non-transitive. So this wouldn't really create a cycle I should be worried about. And really the only cycles I should be worried about are those generated by the relation P itself. And so just to exclude this, I will say that P is acyclic if it creates no cycles. Right, it's as simple as this. And here's the result. Right, here's the main result. Essentially, what this is saying is that acyclicity of the strict preference relation is necessary and sufficient for approximate utility maximization, in the sense that whenever P is acyclic, then this happens if and only if I can find a utility U, I can find a positive threshold delta, such that this correspondence is both gamma monotone in the sense defined previously, and rationalizes my set of observations. Right. So the only content of this model is acyclicity. But the even more crucial observation is this one, that the strict preference relation is still consistent with utility U. Right? This is no longer true for the weak revealed preference relation, unfortunately. So we lose some information, but not all of it. So the strict preference relation is still consistent with the utility function, and this really becomes the foundation for any other result in this paper. Right? So if I want to estimate utilities, if I want to do some welfare analysis, I can use this observation, and that's exactly what I do in the paper. Obviously, I won't be proving it because there's no time for this. It's a short video. Implication 2 to 1, relatively simple. Nothing really very fancy takes place. Implication 1 to 2 is obviously, as it usually is in these papers, that's the main difficulty, to show that 1 actually implies 2. And I want to briefly discuss it because there's one observation I want to highlight. And so proving that 1 implies 2 is done in 2 steps. So let's start with the fact that P is acyclic, that's the assumption. And then in step 1, what I show is that whenever P is acyclic, you can always find a utility function such that that is consistent both with gamma and P, in the sense that if x is in gamma y, then u of x is strictly greater than u of y. If x is strictly preferable to y, then u of x is strictly greater than u of y. That's step 1. Step 2 follows from this proposition, which I want to spend a little time discussing it because I think it's really important for applications. And essentially what this is saying is that take any monotonicity notion of your choosing, take any set of observations that you have, and take any utility that you like. Right, so if you want to talk about risk, you can take expected utility. If you want to talk about ambiguity, you can take savage, or you can take max-min if you like. If you like bundles and you like Cobb-Douglas, you can choose Cobb-Douglas. And once you have your favorite function, check the following: if it's consistent with both gamma and the strict preference relation, then that's a necessary and sufficient condition that guarantees that the same function approximately rationalizes the set of observations for some threshold. In a sense, if you give me your favorite function and you can guarantee that condition 1 holds, then this is equivalent to saying that the same utility function approximately rationalizes the set of observations. Application of this is almost immediate, right? Saying that the main result that was really talking about existence of a utility function can be also used to, in some way, can be applied to checking if a set of observations is approximately rationalizable with a specific utility function. And in the paper, I'm actually doing this, and I'm actually applying this to using some existing results. I'm applying this observation to study of some canonical models of choice under risk and uncertainty. So this is one very important observation that I would really like to highlight. This method is much more flexible and much more general than it would initially seem. And this essentially concludes, this very short video. Main takeaways is that approximate utility maximization is really equivalent to non-transitive indifferences, and that's really it. All right. So if you want to talk about an almost maximizing behavior, what you're really doing is you're really just talking about non-transitive indifferences. Also equivalent to satisficing, even though I never mentioned what I meant by this, but it's a very canonical notion of satisficing, so it wouldn't be really surprising. And I guess maybe there's a little bit. And then finally, elements that were not covered in this talk is based on the equivalence of approximate utility maximization and non-transitive indifferences, based on the main theorem that was just presented. And this observation that strict preference relation is still consistent with the utility function, we can elicit the true preference utility function U, we can make out of sample predictions, we can do welfare analysis and other applications of to other models of choice and other utilities. And that's it. Once again, thank you so much for listening. I hope I didn't take too much of your time. If you have any comments and suggestions, please let me know. You can, here's my website. You can go there. You can find my email. You can download the paper as well. Hopefully, I will hear from you. If not, maybe I will see you on the road at some point. Thank you so much for listening again, and take care.